Alright, here we go. This is acceleration. If you take a look at this slide, you can see on the bottom right hand corner you have the formula for acceleration. Here you can see there's a change in velocity over a certain amount of time. The other picture is a ticker tape diagram, and you can see that the dots are not evenly spaced out, and this represents non-uniform motion. Alright, so what is acceleration? Acceleration is a change in velocity. In this course, you're only going to be worried about the average acceleration, which is a change in velocity over a given time interval, that bullet there. So in this course, acceleration will always be constant and be determined by this equation here, delta v over delta t. So acceleration is a vector. It can be positive or negative. So typically we say that we'll have the right as positive and the left as negative. So the second bullet here, to determine if an object speeds up or speeds down, you have to analyze the direction of the vectors for both motion and acceleration. So for example, if your velocity vector is pointing this way, so you're moving to the right, and your acceleration vector also points in that direction, then you will speed, ignore that, then you will speed up. However, if your velocity vector and your acceleration vector are in opposite directions, then you will speed down. Okay, so acceleration, this third bullet, fully described by both magnitude, how much, and direction, which way. And accelerations are caused by forces, which is the focus of Unit B. So we won't do any forces in this unit, Unit A, but you have to understand that the forces, or pardon me, the accelerations are caused by forces. Also, if the velocity of an object is changing, then it is said to be accelerating. So it could be the magnitude or the direction or both. As long as one of those components is changing or both, then it's acceleration. And we'll come and revisit this idea later when we get to centripetal motion. And the unit is meter per second, or in other words, meter per second square. Okay, so for non-uniform motion, a ticker tape drawing would be an example where the distance traveled in the same time frame is changing. So you can see in this picture that the object is traveling a different amount of distance per same unit time. So what would happen is your position time graph, displacement versus time, would be nonlinear. And your velocity, we can see just by zooming in on this guy, if you were to find the slopes at some key points, what you could do is you could draw in a slope of a tangent line. And we can see that the slopes of these tangent lines are increasing. So if the slopes of a dt graph are increasing, then it's speeding up. So if it's speeding up, then the velocity time graph would be linear increasing. And then the acceleration vector will be, or the acceleration graph will be constant. So here's v versus t, and here's a versus t. Alright, so now we're just going to use the acceleration formula, which is Vf minus Vi over some time frame. So taking the given information, it starts from rest and reaches a final velocity of 10 meters per second east. So if east is positive, its final velocity, Vf, is 10, its initial velocity is 0, and that takes 5 seconds to accomplish that. So we have 10 meters per second per 5 seconds, which is a positive 2 meters per second square. And what this tells us is that every 1 second we will increase, that's what that plus meant, increase 2 meters per second. So every second you gain 2 meters per second. Okay, this one asks us to solve for time for the ball to stop. So when you do your algebra, we need to isolate for time. So the acceleration and the time are going to cross multiply. Like this. So the t and the a, they can cross multiply switch. What's happening here is upstairs on the left goes downstairs on the right, and downstairs on the right goes upstairs on the left. Okay, so Vf, that's the final velocity. How long will it take for the ball to stop? So that would be 0 motion when it's stopped. And then subtracting Vi, and Vi is a positive 5. So we're going to subtract a positive 5 all over the acceleration, which is negative 0.75. So which makes sense if you think about this. If you're traveling to the right and you want to stop, the acceleration has to be the opposite direction. So we have a negative divided by a negative. That'll come out positive. And rounding 6.7 seconds. Okay, we have a positive acceleration vector starting from rest. How long does it take? So again, solving for time. So same formula as last page. How long does it take to reach its takeoff speed? That would be its final velocity. So if you start from rest, you would have to accelerate in the same direction as the acceleration vector. So if our acceleration vector is that way and you're starting from rest, then V final will also be pointing that way. You started from rest, so Vi is 0 all over this 2.5. Okay, we have 70 seconds for this to occur. Now this is an activity that you would do with your group or your pair. So 2 of you at a time, think, pair, share. All I want you to do is go through this list and think about the situation. I'll get you started. So like for the first one, you have positive acceleration. So your acceleration vector points to the right, and you have positive velocity. So your velocity vector points to the right. If they point in the same direction, you speed up. If they point in opposite directions, you speed down. That would be this one here. Okay, so finish that off, and that's it for today.